Okay, listen up. 9 out of 10 students are dropping easy marks on their Cambridge exams, and it is quietly costing them their final grade. You know the drill. They study the theory, they memorize all the definitions, but the second that clock starts ticking, they fall into the exact same traps, year after year. So let's break down the absolute biggest mistake right now before you actually make it.
You really have to beware of the binary addition trap. Think about it. You've got an 8-bit system, you add two numbers together, say 111 and so on, and as those column additions carry a 1 forward each time, eventually a 9th column is created. The total suddenly becomes a binary number consisting of 9 bits, which is, of course, exactly one more than the maximum capacity of an 8-bit system. So what happens next? Well, in an exam, students often just write down those final 8 bits and completely ignore the rest. But in reality, the CPU will literally drop that extra digit, that overflow digit, because it just has nowhere to store it. The computer suddenly thinks that 255 plus 1 equals 0. And that action causes a catastrophic overflow error, meaning there just isn't enough capacity to carry out an instruction, leading to a full system crash. The examiner absolutely wants to see that you understand that consequence, not just the basic math.
All right, let's jump right into Syllabus Area 1, Mastering Packet Switching. To start things off, we need an airtight definition. Packet switching is simply a method where a large message or file is broken up into a number of small, manageable data packets before being sent across a network. It's kind of like taking a massive file and slicing it into smaller puzzle pieces so they can move through the network far more efficiently. Now, to actually secure full marks here, you need a really strict technical methodology. There are 3 crucial steps to follow: diagnose and classify, build the sequence, and then anchor to the context. When an exam asks you about data movement, you simply cannot just write down vague labels. You have to explain the technical process in a clear, logical order that anyone could follow. And then, and this is the real magic key, anchor your explanation to a highly specific context, like a bank system or a robot. Precision over labels is exactly what the examiners are hunting for.
Think of every packet as a little explorer, independently following a different route depending on network traffic and bandwidth availability. But this is exactly why real-time data struggles so much. A time delay is perfectly fine for sending a standard email, sure, but for a real-time video call, if those packets take different routes and arrive too slowly, or just get lost along the way, you get a frozen image. If the packets have to be heavily reassembled into their correct sequence numbers at the destination, you get out-of-sync audio or crazy video lag. This is the exact how and why you've got to include in your exam answers.
Moving along to Syllabus Area 2, Visual Basic Input-Output. Okay, the absolutely crucial point here is avoiding a trap that catches almost everyone: confusing validation with verification. If you mix these two up, it's a guaranteed way to bleed marks. Validation is an automated check performed by the computer itself just to ensure the data entered is reasonable. Verification is entirely different. It's checking if the data accurately matches the original source or intent. Seriously, lock this down in your mind. Do not let these two distinct concepts bleed together. When you're coding in Visual Basic, you need to heavily focus on the logic bridge. Input and output, they're really just the bookends of your algorithm. The real magic, the part the examiner is actually grading you on, is the process that sits right in the middle of them. So many students fall into the trap of writing weak code where they just define an input and an output, but completely fail to show how the data actually functions within a logic-based algorithm. If you just capture user data but don't do any math or decision-making with it in that middle process, you're literally just throwing away easy paper 2 marks.
Let's dive into Syllabus Area 3, Registers and their uses. If you want the absolute maximum score here, you have to prioritize the sequence of mechanisms using a proper winning answer framework. Step 1, identify the question-specific demand. Step 2, classify the key computer science concept. Step 3, sequence the steps of the process logically. And step 4, connect it right back to the context provided in the question. Following this exact order guarantees your answers are going to be crystal clear.
You've got to watch out for what we call floating abstractions. This happens when you just drop an isolated, memorized piece of theory into your exam paper without connecting it to anything real in the question. To get full marks, you have to chain your knowledge directly to the scenario. Don't just generically state that a register holds data temporarily. Explain exactly how that register is being used, specifically in the retail checkout or the banking system the examiner asked you about. You always have to explain the mechanism first and then the consequence to ensure your answer flows perfectly. I want you to be completely honest with yourself for a second. Are you relying on generic rote labels instead of actually explaining the how behind these digital devices? Because just naming a piece of hardware without explaining its process sequence is a major pitfall. We really need to contrast these common mistakes with the high-mark solutions. If your mistake is using vague wording, the solution is swapping that out for precise technical terminology. If your mistake is naming something without explaining it, the solution is detailing the actual process sequence. And if your mistake is just dumping isolated theory, the solution is anchoring your sequential explanation directly to the provided scenarios, like robotics or databases. That framework is your ultimate safety net. Next up is Syllabus Area 4, Embedded Systems Exam Strategy. Let's see how all this builds into a high-scoring answer. Under time-pressured exam conditions, students tend to panic and just describe what an embedded system is. But the examiner wants the reasoning difference. They want an explanation of how it works and exactly why it is used in that context. You have to justify your choice based on its advantages and its mechanical process, not just its definition. To ensure that reasoning is rock solid, we have to train our brains via key contrasts. This is exactly where conceptual bleed happens for a lot of people. Students mix up memory and storage constantly. Just remember, memory is for temporary data retention, while storage is for permanent data retention. If you don't sharply contrast these nearby concepts in your mind right now during your revision, they are 100% going to blur together on exam day. All right, we have covered a ton of ground today, across hardware, programming, and networking. Now it's time to bring all these concepts together for a quick high-mark framework recap. I want you to literally burn this 4-prompt checkpoint into your memory. Before you write down your final exam response, mentally check off these 4 boxes. 1. What is it? Identify the concept. 2. How does it work? Explain the sequence of the mechanism. 3. Where is it used? Anchor it to the scenario. And 4. Why is it chosen? Provide your solid justification. If your answer hits all 4 of those beats, you are definitely securing those top marks. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've got plenty more of these visually driven explainers to get you fully prepped and confident. I'm going to leave you with this final thought as you head back to your revision. When you look at a textbook page tonight, I want you to ask yourself, are you just memorizing the definitions, or are you actually building the mechanisms in your mind? Bridging that gap is the real secret to moving from vague guesses to high-scoring logic. See you in the next explainer.